In 2022, the James Webb Space Telescope opened its eyes and looked deeper into the universe than any instrument in human history. What it found shook the foundations of physics. Scattered across its images were tiny red dots, objects that defied every known category. Not stars, not galaxies, not black holes as we understood them. Something entirely new. Something no model had ever predicted. And when scientists finally decoded what they were, the answer was stranger than anyone imagined. Gigantic balls of gas powered by supermassive black holes at their hearts. A class of cosmic object that had never been seen before, but the red dots were only the beginning. Behind them, the telescope found galaxies that should not exist. Fully formed, fully structured, already dying. In an era when the universe was barely old enough to have produced anything at all. It found an expansion rate that gives two different answers depending on how you measure it. It found evidence that dark energy, the force driving 68% of the cosmos, may be changing. And it found hints that the fundamental constants of physics, the numbers we assumed were eternal and universal, might not be constant at all. Tonight, we are going to follow every crack the James Webb Space Telescope has opened in the Standard Model of the universe. From impossible galaxies to evolving dark energy. From the oldest light in existence to the search for life on distant worlds. By the end, you will understand why some of the most accomplished scientists alive have described this moment not as discovery, but as crisis. The ground is moving, and nobody knows yet where it will settle. If you enjoy our calm nighttime journeys, remember to like and subscribe. We highly encourage our community to discuss the video topics in the comments and react to other comments. It is the most fun when we share our thoughts. Now, let us begin. Tonight we are going somewhere that most science documentaries will not take you. Not to the surface of a planet, not to the inside of a star, but to the moment when the universe stopped making sense. Because over the next 2 hours, we are going to follow a trail of impossible discoveries. Discoveries made by a single telescope floating 1 million miles from Earth. A telescope that was supposed to confirm everything we thought we knew about the cosmos. Instead, it found galaxies that should not exist. Black holes that formed before their own galaxies. An expansion rate that gives two different answers depending on how you measure it. And a force that makes up 68% of everything in existence that appears to be changing in ways no one predicted. By the end of tonight, you will understand why some of the most accomplished scientists alive have described what is happening in cosmology right now, not as excitement, but as vertigo, the feeling of standing on ground you trusted completely and feeling it move beneath your feet. Chapter 1. The red dots that should not exist. In the summer of 2022, just weeks after the James Webb Space Telescope began delivering its first science data, astronomers noticed something unexpected. Scattered through nearly every deep field image the telescope captured were tiny, intensely red points of light. They appeared everywhere the telescope looked. They were compact, they were brilliant, and they were ubiquitous in scenes from the early universe, scenes showing the cosmos as it existed within the first 2 billion years after the Big Bang. Then, roughly 2 billion years into the universe's history, these strange objects vanished from the telescope's view just as inexplicably as they had appeared. Astronomers gave them a nickname, Little Red Dots. The name was informal, almost playful, the kind of shorthand researchers use before they understand what they are dealing with. But the playfulness did not last long. Because as observations accumulated and data piled up, the little red dots refused to fit into any existing category. By 2025, 341 of them had been catalogued, and nobody could agree on what they were. The initial theories were reasonable. Perhaps they were compact galaxies brightened by swarms of newborn stars. Perhaps they were active galactic nuclei, the blazing hearts of young galaxies powered by supermassive black holes, consuming gas and dust at ferocious rates. Both explanations had problems. If they were galaxies full of young stars, they appeared far too massive and too mature for the era they inhabited. The universe simply had not existed long enough to build what these objects seemed to be. And if they were black hole-powered engines, they were missing the signatures that every known active galactic nucleus displays. There were no X-rays. There were no radio waves. These calling cards of feeding black holes were absent. The little red dots looked too massive to be star-forming galaxies and too quiet to be black holes. They were something else, something nobody had predicted. For a time, the little red dots were framed as breaking cosmology itself. They defied practically every expectation set by well-established theories. The mystery deepened with each new observation. Researchers at institutions around the world proposed competing models. Debates played out in journal papers and conference presentations. Some scientists wondered whether the entire framework for understanding the early universe needed to be reconsidered. Then, in January of 2026, a study published in the journal Nature by Darach Watson and colleagues at the University of Copenhagen's Cosmic Dawn Center cracked the mystery open, or at least opened a door. The team had obtained the highest quality spectra ever recorded of a dozen little red dots using the James Webb Space Telescope's near-infrared spectrograph. When they analyzed the light from these objects in unprecedented detail, they found something remarkable. The spectral lines were broadened, but not by velocity. Not by the Doppler effect of gas whipping around a black hole at tremendous speed, which is what astronomers would normally expect. Instead, the broadening was caused by electron scattering. Light was being scattered by an extraordinarily dense cocoon of ionized gas surrounding each object. What this meant was transformative. The little red dots were indeed supermassive black holes. But they were young ones, much less massive than anyone had estimated. Previous calculations based on the assumption that the spectral broadening was caused by velocity had placed these black holes at roughly 1 billion times the mass of our Sun. The new analysis using electron scattering revealed their true masses were 100 times lower, between 100,000 and 10 million times the mass of our Sun. Still enormous by everyday standards, but radically smaller than the earlier estimates suggested. The cocoon of dense ionized gas surrounding each black hole was the key. It was this cocoon that gave the little red dots their distinctive red color. The black hole at the center was consuming gas, generating enormous heat. That heat radiated outward through the cocoon, and the cocoon filtered and reddened the light. Rohan Naidu, an astrophysicist at the Massachusetts Institute of Technology, began calling these objects black hole stars. He and his colleague Anna de Graaf at the Harvard-Smithsonian Center for Astrophysics proposed that they were gigantic luminous balls of gas, powered not by nuclear fusion, the way normal stars operate, but by a supermassive black hole sitting at their center, radiating energy through the surrounding cocoon. Not quite a star and not quite a black hole, but a bit of both. A new class of cosmic object. Something never predicted by any theoretical model. I think this is definitely by far the most exciting thing to come out of the James Webb Space Telescope. Naidu said, "I am fully working on this and setting everything else aside. It is very rare in astronomy that you come across an entirely new class of object, and I am pretty convinced that is the case here. If you start thinking about them now as essentially this enormous star that has a black hole at its center, things start falling into place," he added. The missing X-rays, the absent radio emission, the strange spectral features. All of it makes sense if you stop trying to force these objects into existing categories and accept that they are something genuinely new. But the implications go far beyond reclassifying a set of mysterious dots. If little red dots are cocooned supermassive black holes, they represent a hidden population of growing black holes that previous surveys missed entirely. They are only visible at mid-infrared wavelengths, the exact wavelengths the James Webb Space Telescope was designed to observe. Every previous survey of the early universe was blind to them. Our census of the cosmos in its first 2 billion years was systematically incomplete. We were not seeing the full picture. We were not even close. George Ricke of the University of Arizona put it plainly. The James Webb Space Telescope has shown that our ideas about how supermassive black holes formed were pretty much completely wrong, he said. It looks like the black holes actually get ahead of the galaxies in a lot of cases. That is the most exciting thing about what we are finding. Think about what that means. The Standard Model of Galaxy Formation says that galaxies form first. Gas clouds collapse under gravity. Stars ignite. Over time, the galaxy grows, and at some point, a black hole forms at its center and grows along with it. But the little red dots suggest the opposite may be true. In many cases, the black hole came first. The galaxy grew around it. The entire formation story may need to be flipped. A separate study published in February 2026 by Fabio Paccucci at the Harvard-Smithsonian Center for Astrophysics reinforced this picture from a different angle. Paccucci's team used radiation hydrodynamic simulations to show that the little red dots are best explained as direct collapse black holes. These are objects that form when a massive gas cloud in the early universe bypasses the star formation stage entirely and collapses directly into a black hole. The simulations reproduce the specific characteristics of the little red dots, their weak X-ray emission, the presence of certain metal lines, the absence of star formation features, their abundance, their compact nature, and their evolution over cosmic time. All the puzzling properties of the little red dots are explained within a single self-consistent framework, Paccucci said, without requiring any ad hoc assumptions. Whether they are best described as black hole stars or direct collapse black holes, the conclusion is the same. The early universe was building supermassive black holes faster and more efficiently than anyone imagined. And it was doing it through mechanisms that our models did not account for. But the little red dots are only the latest shock. The very first images the James Webb Space Telescope returned, before anyone knew what a little red dot was, had already sent tremors through the physics community. Because scattered across those images were galaxies that had no right to exist, not one or two, hundreds of them. Galaxies so massive, so structured, so fully formed that they violated the most fundamental predictions of our best model of the universe. And those galaxies are where we are going next. Chapter 2. The Impossible Galaxies. July 12, 2022. The date the universe stopped cooperating. That was the day NASA released the first deep field image captured by the James Webb Space Telescope. The image showed a tiny patch of sky, a region no larger than a grain of sand held at arm's length. But within that grain of sand were thousands of galaxies, clusters of galaxies, arcs of light bent by gravity into shimmering streaks, a window into the deep past of the cosmos, reaching back over 13 billion years. Scientists had expected to see the equivalent of a construction site. The early universe was supposed to be messy, chaotic, half-built. Infant galaxies should have appeared as dim smudges of light, irregular clumps of gas, and young stars struggling to take shape. Instead, what the telescope revealed was a finished product. Enormous, structured, bright galaxies. Galaxies with spiral arms. Galaxies with orderly disks. Galaxies that by every measure appeared mature, fully formed, and ancient in their sophistication. Except they were not ancient. They were young, impossibly young. They existed when the universe was only a few 100 million years old. Imagine pressing play on a time lapse of a skyscraper being built. You expect to see the foundation laid, the steel frame rising floor by floor, the slow, deliberate process of construction. Instead, the very first frame of the video shows the 50th floor already complete. The crane is already on the roof, the lights are already on. That is what the James Webb Space Telescope found. The skyscraper was already there before the construction should have begun. One astronomer described the experience as opening a door, expecting a small room, and finding a continent on the other side. The scale of the surprise was not incremental. It was not a matter of adjusting a few parameters. It was a fundamental mismatch between what every model predicted and what the telescope actually observed. In January of 2026, the situation escalated further. A team led by Rohan Naidu at the Massachusetts Institute of Technology confirmed the most distant galaxy ever observed. Its designation is MOM-Z14. The name comes from the survey that found it, the Mirage or Miracle Survey, designed specifically to test whether these absurdly distant bright galaxies are real or observational artifacts. MOM-Z14 is real. Its redshift was confirmed at 14.44, meaning its light has been traveling through expanding space for about 13.5 of the universe's estimated 13.8 billion years of existence. We are seeing it as it appeared just 280 million years after the Big Bang. That number deserves a pause. 280 million years. In cosmic terms, that is nothing. The universe was an infant, and yet MOM-Z14 is bright. It is compact. It is chemically enriched. It contains nitrogen in quantities that should not be possible so soon after the beginning. Nitrogen is produced inside massive stars and released when those stars end their lives. For nitrogen to appear at these levels, multiple generations of stars had to have formed, burned through their fuel, and scattered their processed elements into the surrounding gas, all within 280 million years. The Standard models said this could not happen that fast. Even more remarkably, MOM-Z14 appears to have cleared its immediate surroundings of primordial hydrogen gas. The early universe was filled with a thick fog of neutral hydrogen, the remnant of the initial conditions. For the fog to clear around a galaxy, that galaxy must produce enough ultraviolet radiation to ionize the hydrogen, breaking it apart atom by atom. This process, called reionization, was supposed to happen gradually over hundreds of millions of years. MOM-Z14 seems to have done it in its own neighborhood, at a redshift where virtually every model predicted the universe should be 100% neutral. It was punching holes in the fog before anyone thought that was possible. With the James Webb Space Telescope, we are able to see farther than humans ever have before, Naidu said. And it looks nothing like what we predicted, which is both challenging and exciting. And MOM-Z14 is not an outlier. The survey that discovered it found that bright galaxies at these extreme distances are roughly 100 times more abundant than pre-launch consensus models predicted. Not 10% more, not double, 100 times more. There is a growing chasm between theory and observation related to the early universe, said Jacob Shen, a postdoctoral researcher at MIT, which presents compelling questions to be explored going forward. But the impossible galaxies are not limited to the most distant ones. At somewhat closer distances, still deep in the early universe, the James Webb Space Telescope found something arguably even more disturbing: dead galaxies. Galaxies that had already stopped forming stars. One of the most striking examples is a galaxy called GS9209. This galaxy formed the vast majority of its stars within the first 800 million years after the Big Bang. It built itself rapidly, aggressively, consuming gas and igniting stars at a furious rate. And then it stopped, completely. By the time the universe was 1.8 billion years old, GS9209 had already gone quiet. Its star formation had ceased. It had lived its entire productive life and shut down before most galaxies in the universe had even started. Picture a neighborhood where homes are being built. The foundations are poured. The frames are going up. It will take years before anyone moves in. And in the middle of this construction zone sits one house that is not only finished, but abandoned. The owner moved in, lived a full life, died of old age, and the house sits empty, all before the neighbors finished pouring their foundations. That is GS9209. It lived and died in an era when the universe itself was barely getting started. Catherine Swarovski of the University of Texas at Austin noted that galaxies like this are supposed to be a rarity, but we are seeing more. So what is going on there? What is going on there indeed? The total stellar mass observed at high redshift, the combined mass of stars in galaxies seen in the early universe, appears roughly 10 times higher than what computer simulations produce when they model galaxy formation using the standard rules. 10 times is not a rounding error. It is not a calibration issue that can be resolved by tweaking a few parameters. It is a structural problem. The simulations are built on the most successful model in the history of cosmology. They incorporate everything we think we know about gravity, dark matter, dark energy, and the physics of gas and stars. And they are producing answers that are wrong by an order of magnitude. Every galaxy the James Webb Space Telescope found in the wrong place at the wrong time was another crack in the foundation. But these cracks were not forming in thin air. They were forming in something specific. A model that had worked with breathtaking precision for decades. A model so successful that scientists had declared an era of precision cosmology, the triumphant phase where the big questions were answered and only the details remained. To understand why these galaxies are impossible, you need to understand what they are impossible according to. The model they defy has a name, it has a history, and until very recently, it had an almost perfect track record. That model is where we are going next. Chapter 3, the model that worked perfectly until now. To understand why the James Webb Space Telescope's discoveries are so disturbing, you need to understand what came before them. You need to understand the model they shattered, because it was not a weak model. It was not a rough guess. It was arguably the most successful mathematical framework in the history of science. It had been tested, refined, and confirmed by decades of observations using every instrument humanity had ever pointed at the sky. And it told a story that was elegant, coherent, and deeply satisfying. The story begins 13.8 billion years ago, with a single, unimaginably hot, unimaginably dense point. Not an explosion in space, but an expansion of space itself. In the first fractions of a second, the universe inflated faster than the speed of light. Within minutes, the first atomic nuclei formed. Hydrogen, helium, trace amounts of lithium. For the next 380,000 years, the universe was a glowing fog, a plasma of charged particles so dense that light could not travel through it. Photons bounced endlessly off free electrons, trapped in a cosmic haze. Then the universe cooled enough for electrons to bind to nuclei, forming neutral atoms. The fog cleared. Light was released. That light has been traveling ever since, stretched by the expansion of space from its original visible frequencies into the microwave range. We call it the cosmic microwave background. It is the oldest light in the universe. A baby photograph of the cosmos taken when it was 380,000 years old. And it is one of the most precisely measured things in all of science. After the fog cleared, there was darkness. The cosmic dark ages. No stars, no galaxies. Just vast clouds of hydrogen and helium drifting through an expanding void. Over hundreds of millions of years, gravity slowly pulled these clouds together. The densest regions attracted more gas. The gas compressed, temperatures rose, and eventually, in pockets scattered across the void, the first stars ignited. Dim, massive, short-lived. They burned through their fuel and scattered heavy elements into the surrounding gas when they died. Those elements, carbon, oxygen, silicon, iron, became the building blocks for the next generation of stars, which formed inside the first primitive galaxies. Those galaxies grew by merging. Small galaxies collided and combined into larger ones. Over billions of years, the mergers produced the grand spirals, the giant ellipticals, the intricate structures we see today. The key word in this story is slowly. The Standard Model predicted a universe that built itself gradually, methodically, from small to large, from simple to complex. Across billions of years of patient gravitational accumulation, this model has a name: Lambda-CDM. Lambda stands for the cosmological constant, the mathematical term representing dark energy, the mysterious force driving the accelerating expansion of the universe. CDM stands for cold dark matter, the invisible substance that provides the gravitational scaffolding on which galaxies are built. Together, Lambda-CDM describes a universe made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. And for decades, Lambda-CDM was untouchable. Its predictions matched observations to an almost eerie degree. The cosmic microwave background, that baby photograph of the universe, showed tiny temperature fluctuations, hot spots and cold spots differing by millionths of a degree. Lambda-CDM predicted the precise pattern of those fluctuations before the most detailed measurements were made. When the European Space Agency's Planck satellite mapped the cosmic microwave background with unprecedented precision, the match with Lambda-CDM was extraordinary. The model predicted where the peaks and troughs in the temperature patterns should be. It predicted their heights and their spacing, and it was right. Point after point after point. The model also predicted the large-scale structure of the cosmos, the cosmic web, a vast network of filaments connecting galaxy clusters with enormous voids in between. Supercomputer simulations running the Lambda-CDM equations produced cosmic webs that matched what surveys of millions of galaxies revealed. The distribution of galaxies across the sky, the sizes of the voids, the densities of the clusters, all matched. Lambda-CDM predicted how far away different types of exploding stars should appear at different distances. It predicted the relative abundances of hydrogen, helium, and lithium produced in the first few minutes after the Big Bang. It predicted the ages of the oldest stars. It predicted the relationship between the mass of galaxy clusters and the temperature of the gas inside them. Observation after observation, measurement after measurement, the model held. Scientists called this era precision cosmology. The big picture was settled. The numbers were known. The story was told. All that remained was to fill in the details. The James Webb Space Telescope was supposed to be the crowning achievement of this era. It was designed to look back to the very first galaxies and watch them forming, catching the universe in the act of building itself from scratch. It was supposed to show us the messy, gradual, small-scale beginnings that Lambda-CDM predicted. Instead, it found the finished product already there. Massive galaxies that had already formed and already died in an era when nothing that large should have existed. Galaxies with spiral structure appearing billions of years before spiral structure was supposed to emerge. Black holes that grew to enormous sizes before their host galaxies had time to form. Stars enriched with heavy elements in quantities that required multiple generations of stellar evolution, packed into a time frame that allowed for at most 1 or 2 generations. The total stellar mass at high redshift, the combined mass of stars found in the earliest galaxies, exceeded the predictions of Lambda-CDM by roughly a factor of 10. That is not a minor correction. That is the model's core prediction, the thing it was specifically built to explain, being wrong by an order of magnitude in the exact era the James Webb Space Telescope was designed to probe. Willem Elbers, a postdoctoral researcher at Durham University and a co-chair of the Cosmological Parameter Estimation Working Group for the Dark Energy Spectroscopic Instrument, captured the mood. For a couple of decades, we have had this standard model of cosmology that is really impressive, he said. As our data are getting more and more precise, we are finding potential cracks in the model and realizing we may need something new to explain all the results together. Something new. That phrase carries enormous weight, because Lambda-CDM is not just a model, it is the foundation on which the entire modern understanding of cosmology is built. The age of the universe, the size of the observable universe, the fate of everything in it, all of these are calculated using Lambda-CDM. If the model is wrong, the answers it gives may be wrong too. And there is a specific number at the heart of this model that governs all of those answers. A number so fundamental that getting it right sets the scale for everything we know about the cosmos. Two groups of scientists have been measuring this number for decades, using two completely different methods. They keep getting two different answers, and the James Webb Space Telescope just confirmed that both of them appear to be right. That number, and the crisis it has created, is where we go next. Chapter 4. The universe is expanding at two different speeds. In 1929, an astronomer named Edwin Hubble sat in his office at the Mount Wilson Observatory in California and looked at data that would change humanity's understanding of its place in the cosmos forever. He had been measuring distant galaxies. Specifically, he had been measuring two things about them: how far away they were and how fast they were moving. And the data told an unmistakable story. Every galaxy he observed was moving away from us, and the farther away a galaxy was, the faster it was receding. The universe was expanding, not the galaxies themselves flying through space like shrapnel from an explosion, but space itself stretching, the fabric of the cosmos growing, carrying the galaxies along with it. It was one of the most profound discoveries in the history of science. Hubble quantified this expansion with a single number: the rate at which the universe is growing. How fast a galaxy at a given distance is moving away from us due to the stretching of space. This number became known as the Hubble constant. It is measured in kilometers per second per megaparsec. A megaparsec is 3.26 million light-years. The Hubble constant tells you that for every megaparsec of distance, galaxies are receding by a certain number of kilometers per second. This number matters more than almost any other measurement in all of physics. Get it right and you can calculate the age of the universe, the size of the observable universe, the total energy budget of the cosmos, and the ultimate fate of everything in it. Get it wrong, and all of those calculations shift. For decades, measuring the Hubble constant was one of the central projects of observational cosmology. And for decades, the measurements were not precise enough to cause concern. Different methods gave slightly different answers, but the error bars were large enough to overlap. Everyone assumed the discrepancies would shrink as instruments improved. Then, the instruments improved, and the discrepancies did not shrink. They sharpened. They solidified. They became a crisis. There are two fundamentally different ways to measure the Hubble constant. The first method looks at the nearby universe. Astronomers identify objects whose intrinsic brightness is known. Certain types of pulsating stars called Cepheid variables, the tip of the red giant branch, a specific stage in stellar evolution. Type 1 are supernovae, exploding stars with a characteristic luminosity. By comparing how bright these objects appear to how bright they actually are, astronomers calculate their distances. Combine those distances with measurements of how fast the galaxies hosting these objects are receding, and you get the Hubble constant. This method, called the distance ladder, gives a value of approximately 73 kilometers per second per megaparsec. The team that has pushed this measurement to its highest precision is the SH0ES collaboration, led by Nobel laureate Adam Riess. Using data from both the Hubble Space Telescope and the James Webb Space Telescope, they have confirmed this value with extraordinary confidence. The second method does not look at the nearby universe at all. It looks at the oldest light in existence, the cosmic microwave background, and extracts from it a detailed picture of the universe when it was only 380,000 years old. Using the Lambda-CDM model, cosmologists then project forward from those initial conditions across 13.8 billion years of cosmic evolution to predict what the expansion rate should be today. The European Space Agency's Planck satellite performed this measurement with stunning precision. The value it gives is approximately 67.4 kilometers per second per megaparsec, 73 versus 67.4. The gap is roughly 9%. In everyday life, 9% is nothing. In fundamental physics, 9% is a chasm. These are two of the most carefully conducted measurements in the history of science. They have been checked, rechecked, scrutinized for errors, repeated with different instruments, and subjected to every form of analysis the scientific community can devise. And they refuse to agree. This disagreement is called the Hubble tension. And in 2025, at a meeting of the American Astronomical Society, Duke University astrophysicist Dan Skolnick declared that the Hubble tension had become a Hubble crisis. The James Webb Space Telescope was supposed to help resolve this. In 2024 and 2025, the SH0ES team used the telescope's superior resolution to observe the same Cepheid variable stars that the Hubble Space Telescope had measured. The concern had always been that Hubble's older instruments might be blurring the starlight, introducing errors through a phenomenon called crowding, where nearby stars blend together and make individual measurements less reliable. The James Webb Space Telescope's sharper vision would either confirm or correct the Cepheid measurements. It confirmed them. The local value of the Hubble constant held firm at approximately 73. The crowding concern was ruled out at high statistical confidence. The measurement was robust. Then in May of 2025, Wendy Friedman's Chicago Carnegie Hubble program published results using a different technique calibrated with the James Webb Space Telescope. Instead of Cepheid variables, Friedman's team used the tip of the red giant branch method. Their result came in at approximately 70.4, with error bars of about 3%. Friedman argued that this result was consistent with the cosmic microwave background value and that the tension was resolving. The community erupted. Critics pointed out that Friedman's measurement relied on calibration from a single galaxy. The error bars were wide enough to overlap with both the SH0ES value and the Planck value, which meant the measurement was consistent with everything and therefore resolved nothing. Dan Skolnick noted that the result sits in the middle of the Hubble tension and expressed surprise that anyone would claim it rules the tension out. Then, in December 2025, a completely independent measurement arrived. The TD Cosmo collaboration used a technique called time delay cosmography. When light from a distant quasar passes near a massive galaxy, gravity bends it, creating multiple images of the same quasar. Because each image's light travels a slightly different path, the images flicker at slightly different times. By measuring these time delays with exquisite precision, astronomers can calculate the expansion rate without relying on any of the traditional methods. The TD-COSMO result, based on 8 gravitational lens systems, observed with some of the most advanced telescopes available, came in at approximately 71.6 kilometers per second per megaparsec. Closer to the local measurements than to the cosmic microwave background value, Kenneth Wong of the University of Tokyo, a member of the TD-COSMO collaboration, stated it plainly: "Our measurement is completely independent of other methods, both early and late universe, so if there are any systematic uncertainties in those, we should not be affected by them." The tension persists. Multiple independent methods measuring the nearby universe consistently give higher values than the prediction derived from the early universe. The statistical significance of the disagreement has reached 5 sigma, the gold standard threshold in physics, meaning the probability of this discrepancy being a random fluke is roughly 1 in 3.5 million. If both measurements are correct, and the evidence increasingly suggests they are, then either our model of the early universe is wrong, or our understanding of how the universe evolved from then to now is wrong. There is no comfortable middle ground. Some theorists have proposed early dark energy, a brief burst of extra dark energy in the infant universe that would have altered the expansion rate before the cosmic microwave background formed. Others point to new neutrino physics or exotic dark sector interactions. Whatever the answer turns out to be, one thing is clear. The most precisely measured number in cosmology is giving 2 incompatible answers. And the thing that holds every galaxy together, the invisible scaffolding on which the entire structure of the universe is built, is now under scrutiny too, because the James Webb Space Telescope is finding galaxies so massive that the scaffolding should not have been ready for them. That scaffolding, and the mystery of what it is actually made of, is where we go next. Chapter 5: The Invisible Scaffolding. There is something holding the universe together that we cannot see. We cannot touch it. We cannot photograph it. No instrument has ever detected a single particle of it directly. And yet without it, nothing we observe makes sense. Not the rotation of galaxies, not the bending of light around massive objects, not the web of cosmic structure stretching across billions of light years, not even the existence of the very galaxies where stars and planets form. Without this invisible substance, the universe as we know it would fly apart. We call it dark matter. The name is misleading. It is not dark in the way a shadow is dark. It does not absorb light or block it. It is dark because it does not interact with light at all. It passes through ordinary matter as if it were not there. It produces no electromagnetic radiation of any kind, no radio waves, no infrared, no visible light, no X-rays, no gamma rays, nothing. It is utterly transparent to every form of detection we have ever devised, and yet it accounts for roughly 27% of the total energy content of the universe, more than 5 times the amount of ordinary matter, the protons and neutrons and electrons that make up everything we can see and touch. The evidence for dark matter is overwhelming and comes from multiple independent lines of observation. The first clue arrived in the 1930s, when astronomer Fritz Zwicky measured the velocities of galaxies within the Coma cluster. The galaxies were moving too fast. Based on the visible mass in the cluster, they should have drifted apart long ago. Something unseen was holding them together. Something massive. Something invisible. The evidence sharpened dramatically in the 1970s when Vera Rubin and Kent Ford measured the rotation speeds of stars in spiral galaxies. Stars at the outer edges of galaxies were orbiting just as fast as stars near the center. This made no sense if the visible stars and gas were the only source of gravity. In any system governed by Newtonian physics, objects farther from the center of mass should orbit more slowly. The outermost planets in our solar system move more slowly than the inner ones. Mercury orbits the Sun faster than Neptune does. But in galaxy after galaxy, Rubin and Ford found flat rotation curves. The outer stars refused to slow down. The only explanation that fit was a massive halo of invisible matter surrounding each galaxy, extending far beyond the visible disk, providing additional gravitational pull that kept the outer stars moving at their observed speeds. Then came gravitational lensing. Einstein's general theory of relativity predicts that massive objects warp the fabric of space-time, bending the paths of light passing near them. Astronomers observed that light from distant galaxies was being bent around galaxy clusters in ways that required far more mass than the visible matter could account for. The invisible mass was acting as a lens, focusing light from behind it. Mapping the distortions allowed astronomers to map the distribution of dark matter, creating images of something invisible by observing its gravitational effect on light. The cosmic microwave background provided yet another line of evidence. The precise pattern of temperature fluctuations in the oldest light requires dark matter to explain the acoustic peaks, the characteristic spacings in the power spectrum. Without dark matter, the peaks are in the wrong places at the wrong heights. With dark matter, they match the observations perfectly. So dark matter exists. The evidence is as strong as the evidence for many things we consider established facts of physics. But what is it that remains one of the deepest unsolved questions in science? Despite decades of experiments using underground detectors shielded from cosmic rays, particle accelerators smashing protons together at nearly the speed of light, and satellite observatories scanning the sky for signs of dark matter annihilation, not a single dark matter particle has been directly detected. We know it is there. We do not know what it is. What we do know is how it shapes the universe. Dark matter forms the scaffolding on which everything visible is built. In the Standard Model of Cosmology, dark matter halos form first. In the early universe, slight fluctuations in the density of dark matter, seeded by quantum variations in the first moments after the Big Bang, grew under gravity into increasingly dense clumps. These clumps, called halos, attracted ordinary gas. The gas fell into the gravitational wells created by the dark matter, compressed, cooled, and eventually ignited into stars. The first galaxies formed inside dark matter halos. The halo was the foundation. The galaxy was the building constructed on top of it. Halos grew by merging. Small halos combined into larger ones. When halos merged, the galaxies inside them merged too. Over billions of years, this hierarchical process built the structures we see today, from dwarf galaxies to the massive clusters containing thousands of galaxies. This is the bottom-up model of structure formation. It is one of the great achievements of Lambda-CDM, and the James Webb Space Telescope is breaking it. The galaxies the telescope is finding in the early universe are too massive for the halos that should have been available at that time. The halos grow by a process that takes time. Dark matter particles interact gravitationally, but slowly at cosmic scales. Small halos must form first, then merge again, building up to sizes capable of hosting large galaxies. The timeline is set by the physics of gravitational collapse. It cannot be rushed, but the James Webb Space Telescope is finding galaxies that look as if they were built on foundations that should not have been ready. Imagine arriving at a construction site where the building is already standing, but the foundation was poured yesterday. The concrete has not had time to set. The rebar has not been tied. The footing has not cured. And yet, there stands a 50-story tower. This presents three uncomfortable possibilities. The first is that dark matter halos formed more efficiently in the early universe than our simulations predict. Perhaps there are physical processes we have not accounted for that accelerated halo growth. If so, our simulations need adjusting, but the basic framework survives. The second possibility is that dark matter behaved differently at the extreme temperatures and densities of the early universe. Perhaps its properties changed. Perhaps it interacted with itself or with ordinary matter in ways it no longer does. Self-interacting dark matter models propose exactly this. If dark matter particles have weak interactions with each other, the internal structure of halos would be different, potentially allowing faster galaxy formation. The third possibility is the most radical. Dark matter may not be what we think it is at all. It may not be a particle. It may not be a substance. It may be a modification of gravity itself, an alteration in the way gravity works at very large scales or very low accelerations. This idea, once considered fringe, has gained traction since the James Webb Space Telescope began delivering data. Each possibility carries different implications. The first requires tuning, the second requires new physics. The third requires rebuilding the foundation of cosmology from scratch. But there is something even older than the galaxies, older than the stars, older than the dark matter halos themselves. A faint glow that has been traveling for 13.8 billion years, the cosmic microwave background, the oldest light in the universe. And hidden in its temperature patterns are anomalies that have been whispering for years, anomalies that the James Webb Space Telescope is making increasingly difficult to dismiss. Those anomalies, and what they might mean, are where we turn next. Chapter 6: The Oldest Light and Its Hidden Patterns. 380,000 years after the Big Bang, the universe did something extraordinary. It became transparent. For the first time since the beginning, light could travel freely through space. Before that moment, the cosmos was a seething plasma. Electrons and protons careened through a fog of energy so dense that photons could not travel more than a short distance before colliding with a charged particle and bouncing off in a random direction. The universe glowed, but it was opaque. Light was trapped. Then the temperature dropped below roughly 3,000 degrees. Electrons slowed enough to be captured by protons, forming neutral hydrogen atoms. The fog cleared. The photons that had been bouncing around inside the plasma were suddenly free. They streamed outward in every direction, and they have been traveling ever since. That light is still here. It fills the universe. It comes from every direction in the sky. It has been stretched by 13.8 billion years of cosmic expansion, from its original visible and infrared wavelengths into the microwave range. We call it the cosmic microwave background, and it is the single most important piece of evidence in all of cosmology. In 1965, Arno Penzias and Robert Wilson at Bell Laboratories in New Jersey accidentally detected it while calibrating a radio antenna. They could not eliminate a persistent background hiss coming from every direction. They cleaned pigeon droppings off the antenna. They checked every cable and connection. The hiss remained. It was the echo of creation itself. They received the Nobel Prize. Since then, the cosmic microwave background has been mapped with increasingly precise instruments. The Cosmic Background Explorer satellite in 1989, the Wilkinson Microwave Anisotropy Probe in 2001, the Planck satellite in 2009. Each generation of instruments revealed the picture in finer detail. And what the picture shows is breathtaking. The cosmic microwave background is almost perfectly uniform. Its temperature across the entire sky is 2.725 Kelvin, just a few degrees above absolute zero. But embedded in that uniformity are tiny variations. Temperature fluctuations of roughly 1 part in 100,000. Hot spots and cold spots differing by millionths of a degree. These fluctuations are the seeds of everything. The slightly denser regions in the infant universe that would eventually, over billions of years, gravitationally attract enough matter to become galaxy clusters. The slightly less dense regions that would become the vast cosmic voids. Every structure in the observable universe traces its origin to these microscopic temperature differences in the oldest light. The match between the observed fluctuations and the predictions of Lambda-CDM was one of the great triumphs of modern science. The model predicted the precise statistical pattern of the hot and cold spots, their sizes, their relative intensities, the characteristic spacings between peaks in what physicists call the power spectrum. The Planck satellite confirmed the predictions to extraordinary accuracy. It was as if someone had written down the answer before opening the envelope. And the answer was right to several decimal places. But the cosmic microwave background is not entirely clean. Hidden within its near-perfect patterns are anomalies that have puzzled cosmologists for over 2 decades. Anomalies that were noticed, flagged, debated, and in many cases set aside as probable statistical flukes. Anomalies that the James Webb Space Telescope is making harder to ignore. The first is the cold spot. A region in the constellation Eridanus where the cosmic microwave background temperature is significantly lower than the surrounding sky. The cold spot is not just slightly cooler. It is cooler in a way that is statistically unexpected given the predictions of Lambda-CDM. It is too cold, too large, and too well defined. Multiple explanations have been proposed. A supervoid, an unusually empty region of space along the line of sight. A texture, a topological defect from a cosmic phase transition. Statistical noise. None has been universally accepted. The second anomaly is more unsettling. It is called the axis of evil, a name given only half in jest by cosmologists who first noticed it. When the large-scale temperature patterns in the cosmic microwave background are analyzed, they show an unexpected alignment. The largest fluctuations are not randomly oriented, as a universe born from a uniform explosion should produce. They are aligned along a preferred direction in the sky. A universe that began as a random quantum fluctuation, inflating outward in all directions, should have no preferred direction. The isotropy principle, the assumption that the universe looks the same in every direction at large scales, is one of the foundational pillars of cosmology. The axis of evil challenges it. For years, these anomalies were treated as curiosities, interesting but not alarming. The error bars were large enough, the statistical significance ambiguous enough, that most cosmologists could continue working within the standard framework without losing sleep. Then the James Webb Space Telescope began mapping galaxies at unprecedented distances. And when researchers overlaid the telescope's galaxy maps onto the cosmic microwave background anomalies, something uncomfortable emerged. The distribution of early galaxies showed correlations with the anomalous regions. The pattern of galaxy clustering at high redshift appeared connected to the patterns in the oldest light, not perfectly, not conclusively, but suggestively. Perhaps the seeds of galaxy formation were not as random as assumed. Perhaps conditions during or before the moment of recombination, the moment the cosmic microwave background was released, were more complex than the Standard Model accounts for. Perhaps exotic energy forms influenced the primordial plasma. Perhaps the initial conditions of the Big Bang itself were not the simple uniform inflation that Lambda-CDM assumes. It may be nothing. It may be the most important coincidence in the history of cosmology. But when you zoom out far enough, when you step back and look at the universe at the very largest scales, the anomalies in the oldest light connect to something visible. A structure so vast it stretches across billions of light years. A structure that, according to our best models, should not exist. The cosmic web itself, and the impossible structures embedded within it, is where we are heading next. Chapter 7. The cosmic web and the structures too big to exist. If you could step outside the universe and look at it from a distance, the way you might look at a city from an airplane, you would see something astonishing. The universe is not a random scattering of galaxies. It has architecture. A structure so vast and so intricate that it took supercomputers decades to simulate and surveys of millions of galaxies to confirm. Galaxies are not evenly distributed through space. They are strung along enormous filaments, threads of dark matter and gas stretching hundreds of millions of light-years in length. Where filaments intersect, galaxy clusters form, dense knots of thousands of galaxies bound together by gravity. Between the filaments lie voids, enormous empty regions where almost nothing exists. Some of these voids are hundreds of millions of light-years across. Spaces so empty that a photon could cross them and encounter almost nothing. Together, the filaments, the clusters, and the voids form what cosmologists call the cosmic web. It is one of the most beautiful structures in nature, and it is one of the great triumphs of the Lambda-CDM model. Supercomputer simulations that begin with the tiny density fluctuations imprinted in the cosmic microwave background and evolve them forward through billions of years of gravitational interaction, produce cosmic webs that match observations with remarkable fidelity. The sizes of the filaments, the densities of the clusters, the emptiness of the voids, the statistical properties of the whole network, all match. This was considered one of the strongest confirmations that Lambda-CDM describes the real universe. But even here, at the largest scales, the James Webb Space Telescope is finding discrepancies. It has discovered protoclusters, the precursors of galaxy clusters, at much earlier times than models predict. These protoclusters are further along in their development than they should be. They contain more galaxies, more organized structure, more gravitational binding than the standard simulations produce for those epochs. Think of it like a time-lapse of a farming landscape developing into a city. The model says that after 10 years, you should see a few small villages scattered across the countryside, dirt roads connecting them, fields in between. What the James Webb Space Telescope found was the outline of a metropolitan area already roughed in, roads paved, districts forming, infrastructure partially in place. The city was assembling itself faster than the model said was possible, and the cosmic web has an even bigger problem, not at the small scale of individual protoclusters, but at the very largest scale. The cosmological principle, the assumption that the universe is homogeneous and isotropic at sufficiently large scales, places a theoretical limit on how large a gravitationally bound structure can be. Based on the age of the universe and the speed at which gravity can pull matter together, the largest coherent structure should be no more than roughly 1.2 billion light-years across. Anything larger would require more time to form than the universe has existed, and yet astronomers have found structures that dwarf this limit. The Hercules Corona Borealis Great Wall, identified through the distribution of gamma-ray bursts, appears to be roughly 10 billion light-years across. The giant arc, discovered in 2021 through the analysis of quasar absorption systems, spans approximately 3.3 billion light-years. The Sloan Great Wall stretches over 1.3 billion light-years. Each of these exceeds the theoretical ceiling. The standard response is observational bias. Perhaps these structures are not truly gravitationally bound. Perhaps they are chance alignments, statistical artifacts created by the particular way we observe the sky. The matter within them may not be physically connected in the way a galaxy cluster is connected. It may simply look that way from our vantage point. This is a reasonable objection. Observational cosmology at the largest scales is extraordinarily difficult. Disentangling real structure from projection effects, selection biases, and the particular geometry of our surveys is a challenge that every large-scale structure study must grapple with. But the objection has limits. If every anomalously large structure were a statistical artifact, we would not expect to keep finding more of them. And the James Webb Space Telescope keeps finding evidence that structure formed faster and organized itself earlier than the Standard Model predicts, not just at the scale of individual galaxies, but at the scale of their clustering, their filamentary connections, and their large-scale distribution. If the cosmological principle is even slightly wrong, if the universe is not perfectly homogeneous at the largest scales, the consequences cascade through everything. The age of the universe is calculated, assuming homogeneity. The expansion rate is measured assuming isotropy. The dark energy measurements depend on the assumption that space looks the same in every direction. Loosen any of these assumptions and the numbers shift. Most researchers still believe the cosmological principle holds to a sufficient approximation. The anomalies may have conventional explanations. The structures may be statistical flukes. The protoclusters may simply require better simulations. But the list of things that require conventional explanations is growing. And each new item added to the list adds weight to the alternative possibility that something fundamental about the model is incomplete. The scaffolding may be wrong. The ancient light has anomalies. The structures are too big. And now we come to the force that drives it all. The force that makes up 68% of everything in the universe. The force that is pushing the cosmos apart at an accelerating rate. The force we named but never understood, dark energy. And a massive new survey has just delivered results that suggest we got that wrong too. Chapter 8. Dark energy is changing. In 1998, two teams of astronomers made the same discovery independently. They were measuring the distances to a specific type of exploding star, Type 1, a supernovae. These explosions are useful because they all reach roughly the same peak brightness, which means you can calculate how far away they are by measuring how dim they appear. The teams expected to find that the expansion of the universe was slowing down. Gravity should be pulling everything back together. The rate of expansion should be decelerating. Instead, they found the opposite. The expansion was accelerating. Distant supernovae were dimmer than expected, meaning they were farther away than they should have been. The universe was not just expanding, it was expanding faster and faster. Something was pushing it apart. That something was given the name dark energy. It was not a discovery in the traditional sense. Nobody found a particle. Nobody detected a force. What the astronomers found was an absence, a gap between what gravity predicted and what the universe was doing. Dark energy is the name we gave to whatever fills that gap. The simplest description of dark energy is the cosmological constant. Albert Einstein first introduced this concept in 1917, adding it to his equations of general relativity to allow for a static universe. When Hubble discovered the expansion, Einstein dropped the constant, reportedly calling it his greatest blunder. But when the accelerating expansion was discovered 80 years later, the cosmological constant came roaring back. In its modern form, it represents a fixed energy density built into the fabric of space-time itself. Every cubic meter of space, no matter where it is or what it contains, has the same tiny amount of energy. As space expands, new space is created, and the total amount of dark energy increases. This constant pressure drives the acceleration. The cosmological constant is elegant. It is simple. It requires only one number, and it has a devastating problem. When theoretical physicists try to calculate the energy of empty space using quantum mechanics, they get a number that is catastrophically wrong. Not slightly wrong. Not wrong by a factor of 10 or 100. Wrong by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It is the largest discrepancy between theory and observation in the history of science. Quantum mechanics predicts that empty space should be seething with so much energy that the universe would have torn itself apart in the first fraction of a second after the Big Bang. Obviously, it did not. Something is cancelling almost all of that energy, but not quite all of it. A tiny residue remains, and that residue is what we call dark energy. Nobody knows why. Nobody has a satisfying explanation for why the cosmological constant has the value it does. It is one of the deepest unsolved problems in fundamental physics. But for decades, the working assumption has been that whatever dark energy is, it is constant. It does not change over time. It does not evolve. It is a fixed feature of space-time itself. That assumption may now be wrong. In March of 2025, the Dark Energy Spectroscopic Instrument, known as DESI, released the results of its second major data analysis. DESI is a remarkable machine. Mounted on the Nicholas U. Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona, it can capture the spectra of 5,000 celestial objects simultaneously using a robotic array of fiber optic cables. Over its first 3 years of operation, it has mapped the three-dimensional positions of nearly 15 million galaxies and quasars, constructing the largest three-dimensional map of the universe ever made. DESI measures the expansion history of the universe by tracking a phenomenon called baryon acoustic oscillations. In the early universe, sound waves traveling through the primordial plasma left an imprint on the distribution of matter, a characteristic spacing, like the rings left by a pebble dropped in a pond. That spacing serves as a standard ruler. By measuring the apparent size of the ruler at different distances, which correspond to different epochs in cosmic history, astronomers can track how the expansion rate has changed over the past 11 billion years. When the DESI team combined their measurements with data from the cosmic microwave background, supernovae observations, and weak gravitational lensing surveys, the results were striking. The standard Lambda-CDM model, in which dark energy is a fixed cosmological constant, struggled to fit all the datasets simultaneously. The data preferred a model in which dark energy is not constant, a model in which the influence of dark energy has been weakening over time. The statistical significance of this preference ranged from 2.8 sigma to 4.2 sigma, depending on which combination of datasets was used. 4.2 sigma means the probability of the result being a statistical fluke is roughly 1 in 40,000. That is not yet the 5 sigma gold standard that physics requires to claim a discovery. But it is mounting, and it is getting stronger with more data. Will Percival, co-spokesperson for DESI and a professor at the University of Waterloo, captured the significance. "We are guided by Occam's razor," he said, "and the simplest explanation for what we see is shifting. It is looking more and more like we may need to modify our standard model of cosmology to make these different datasets make sense together, and evolving dark energy seems promising." Willem Elbers, a postdoctoral researcher at Durham University who co-chairs DESI's Cosmological Parameter Estimation Group, added context. "For a couple of decades, we have had this standard model of cosmology that is really impressive. As our data are getting more and more precise, we are finding potential cracks in the model and realizing we may need something new to explain all the results together. If dark energy is not constant, it has a different name: quintessence, a dynamic field that evolves over cosmic time, sometimes stronger, sometimes weaker. Its behavior governed by physics we have not yet identified. Quintessence models have existed in theoretical physics for decades, but they were always the less favored option. The cosmological constant was simpler, and in science, simpler usually wins until the data force you somewhere more complicated. The implications of evolving dark energy are profound. If dark energy has been weakening, the universe's past looks different than Lambda-CDM predicts. The rate at which structure formed, the timing of galaxy assembly, the relationship between the early universe and the present, all of these shift, and the universe's future changes too. Under a constant cosmological constant, the universe expands forever, accelerating until every galaxy beyond our local group recedes past the cosmic horizon and the sky goes dark. Under evolving dark energy, other fates are possible. If dark energy continues to weaken, the acceleration may slow. If it reverses sign, the universe could begin to contract. The end of the cosmos is not yet written. Mustafa Ishak Baushaki, a professor at the University of Texas at Dallas who has studied cosmic acceleration for 25 years, called the moment significant. If the evidence continues to grow, this will be huge for cosmology and all of physics, he said. The DESI results do not prove that dark energy is evolving. Not yet. The 5 sigma threshold has not been crossed. Future data releases, expected as DESI completes its 5-year survey, will either strengthen the signal or watch it fade, but the direction is clear. The simplest model is under pressure, and that pressure connects to an even deeper question. If dark energy can change, perhaps other things we assumed were fixed are not fixed either. Perhaps the very constants of physics, the numbers that govern how atoms behave, how light travels, how forces interact, are not constant at all. That possibility, and what it would mean for everything we think we know, is where we go next. Chapter 9. What if the laws of physics are not constant? Everything in physics rests on a set of numbers: the speed of light, the gravitational constant, the charge of the electron, the mass of the proton. These numbers appear in virtually every equation that describes how the universe works. They govern how atoms absorb and emit light, how forces attract and repel, how particles combine to form matter, how matter organizes itself into stars and planets and people. Change any one of these numbers by even a tiny fraction, and the universe becomes unrecognizable. Atoms do not form. Stars do not ignite. Chemistry does not work. Life does not exist. These numbers are called fundamental constants, and the deepest assumption in all of physics, an assumption so foundational that most scientists never even think to question it, is that these constants are the same everywhere in the universe and have been the same at every moment since the beginning of time. The speed of light in a galaxy 10 billion light-years away is the same as the speed of light in your living room. The charge of the electron in the first second after the Big Bang was the same as the charge of the electron today. The laws of physics are universal and eternal. But what if they are not? Among the fundamental constants, one plays a particularly important role in cosmology. It is called the fine structure constant. It is a dimensionless number, meaning it has no units. Its value is approximately 1 divided by 137, and it governs the strength of the electromagnetic force, the force that determines how charged particles interact, how atoms absorb and emit photons, how chemical bonds form, how light behaves. Because the fine structure constant determines how atoms interact with light, it leaves a fingerprint on every spectrum ever measured. When light from a distant galaxy or quasar passes through intervening clouds of gas, the atoms in those clouds absorb specific wavelengths. The pattern of absorption lines is determined in part by the fine structure constant. If the constant had a different value when that light was absorbed, billions of years ago in a galaxy far away, the absorption lines would shift slightly from their expected positions. In the early 2000s, a team led by John Webb at the University of New South Wales in Australia analysed absorption spectra from distant quasars observed with the Keck telescope in Hawaii. They found hints that the fine structure constant might have been slightly different in the past, slightly smaller. The variation was tiny, less than 1 part in 100,000, but it was there, and it was statistically significant. The result was immediately controversial. Other teams using different telescopes and different analysis methods found conflicting results. Some confirmed the variation. Others found no evidence of it. The debate has continued for over 2 decades. Then, something even stranger emerged. When Webb's team combined data from the Keck telescope in the Northern Hemisphere with data from the Very Large Telescope in Chile, which observes the southern sky, they found that the variation was not uniform. It was directional. The fine structure constant appeared to be slightly larger in one direction of the sky and slightly smaller in the opposite direction, a dipole pattern. As if the universe had a preferred axis along which the laws of physics varied. A truly universal constant should not vary with direction. If it does, the implications are staggering. The universe would not be isotropic at the deepest level. The laws of physics would depend on where you are and which direction you are looking. The foundational assumption of modern cosmology, that the universe is the same everywhere, would be broken. The James Webb Space Telescope has the spectroscopic precision to test these earlier hints with unprecedented sensitivity. Its near-infrared spectrograph can measure absorption lines in distant quasars with far greater accuracy than any previous instrument. Early results have not yet confirmed or refuted the variation, but the telescope is now being used specifically to target this question. If JWST detects a variation in the fine structure constant at the level previously suggested, it would be one of the most consequential measurements in the history of physics. And the fine structure constant is not the only constant under scrutiny. The proton-to-electron mass ratio, another dimensionless constant that determines how molecules absorb light, has also been tested using distant quasar spectra. Some studies have reported hints of variation, though again the results are contested. Now consider what it would mean if these constants were different in the early universe. Every prediction we have made about the first galaxies, the first stars, the cosmic microwave background, and the evolution of cosmic structure assumes that the laws of physics were the same then as they are now. The chemical reactions that governed star formation, the nuclear processes that built heavy elements inside stellar cores, the atomic physics that determined how the primordial plasma cooled and released the cosmic microwave background. All of these depended on the fundamental constants having their current values. If the fine structure constant was even slightly different in the early universe, atoms would have absorbed and emitted light at different frequencies. The cooling rates of gas clouds would have been different. The opacity of the early universe would have been different. The timing of recombination, the moment when the cosmic microwave background was released, would have shifted. The entire thermal history of the cosmos would change. This could explain why the early galaxies look wrong. Our models assume fixed constants. If the constants were different, our predictions for the early universe would be systematically off. Not because the model is structurally flawed, but because one of its deepest assumptions, so deep that it is rarely even stated explicitly, is incorrect. The implications extend beyond cosmology. If the laws of physics are not constant, they are not laws in the traditional sense. They are parameters. Values that happen to have their current settings, but could in principle have been different, and perhaps were different in the past. This idea connects to some of the deepest questions in theoretical physics. String theory predicts a vast landscape of possible universes, each with different values for the fundamental constants. The multiverse hypothesis suggests that our universe is one of an enormous, perhaps infinite, number of universes, each with its own set of physical laws. If the constants can vary within our own universe, even slightly, it provides the first observational evidence that the laws of physics are not carved into the bedrock of reality, but are features of a particular cosmic environment. Whether or not the constants vary, one fact remains inescapable. 95% of the universe is something we cannot see, cannot directly detect, and cannot explain. Dark matter and dark energy, together, make up the overwhelming majority of everything that exists. And the James Webb Space Telescope has just shown that even the 5% we thought we understood, the ordinary matter that makes up stars and galaxies and planets and people, does not behave as our models predicted. The math of that compounds in a direction nobody finds comfortable, and that uncomfortable arithmetic is where we turn next. Chapter 10. The 95% we do not understand. Let us take inventory. Let us count up everything in the universe and see what we actually know. Ordinary matter. The protons, neutrons, and electrons that make up everything you have ever seen, touched, tasted, or measured. Every star, every planet, every cloud of gas, every grain of dust. Every molecule in your body. Every atom in every object on Earth. All of it. The total contribution of ordinary matter to the energy budget of the universe is approximately 5%. 5%. That is everything we understand. Everything physics can describe in detail. Everything chemistry can analyze. Everything biology can study. 5%. Dark matter contributes roughly 27%. We know it exists because of its gravitational effects. We can map its distribution using gravitational lensing. We can infer its properties from galaxy rotation curves and the structure of the cosmic web. We know it is not ordinary matter. We know it does not interact with light. We know it clumps together under gravity. Beyond that, we are largely in the dark. Decades of experiments designed to detect dark matter particles directly have found nothing. The Large Hadron Collider at CERN has searched for dark matter candidates in the debris of high-energy proton collisions. Nothing. Underground detectors, shielded by miles of rock, designed to catch the rare interaction between a dark matter particle and an ordinary atom, have recorded no confirmed signal. We have a name. We have a mathematical description. We do not know what it is. Dark energy contributes roughly 68%. We know even less about it than we know about dark matter. We know it is driving the accelerating expansion of the universe. We know it appears to be smoothly distributed through space. We know its energy density is approximately constant over the timescales we can measure, though as we discussed, new evidence suggests it may be evolving. We do not know what it is. We do not know why it has the value it does. We do not know if it is a property of space-time itself, or a new form of energy, or something else entirely. Add it up. 95% of everything in the universe is something we cannot see and cannot explain. We have names for it. We have equations that describe its behavior, but we do not know what it is. We are like someone who can describe the wind in perfect mathematical detail, predict its speed and direction and temperature with extraordinary precision, but has never seen air and has no idea what it is made of. Now here is the compounding problem. Our understanding of the 5%, the ordinary matter, depends heavily on our understanding of the 95%. The way galaxies form depends on dark matter. The rate at which the universe expands depends on dark energy. The predictions of Lambda-CDM for how galaxies should look at any given epoch depend on getting the dark matter and dark energy parts right. If our mathematical descriptions of dark matter or dark energy are even slightly off, the errors propagate into our predictions for the visible universe. Think of it as a building with 3 floors. The ground floor is dark energy. The second floor is dark matter. The third floor is ordinary matter. If the ground floor shifts by even a small amount, the second floor moves. And if the second floor moves, the third floor moves too. Small errors at the bottom compound into larger errors at the top. This is the crisis of cosmological precision. As our instruments become more precise, they are revealing not just the universe more clearly, but the edges of our understanding more sharply. The James Webb Space Telescope has brought the edges into focus with uncomfortable clarity. The early galaxies are too massive. The expansion rate disagrees with itself. Dark energy may be evolving. Structures are too large. The cosmic microwave background has unexplained patterns. Each of these anomalies might have a simple, conventional explanation, but they all push in the same direction. They all suggest that something about the foundational model is incomplete, and there is one more piece of the puzzle that deepens the mystery. The first stars. Population 3 stars. The theoretical first generation of stars that ignited in the cosmic dark ages, hundreds of millions of years after the Big Bang. These stars have never been directly observed. They are predicted to have been enormous, hundreds of times more massive than anything in the universe today, made entirely of hydrogen and helium, with no heavy elements whatsoever, because no heavy elements existed yet. They burned hot, burned fast, and when they died, they scattered the first heavy elements into the surrounding gas, seeding the next generation of stars with the raw materials for planets, chemistry, and eventually, life. The James Webb Space Telescope has not found population 3 stars directly, but it has found something unexpected in the earliest galaxies. Levels of heavy elements that are higher than they should be. Chemical enrichment that happened faster than models predict. The galaxy MOM-Z14 at redshift 14.44 shows nitrogen in quantities that should not be possible, just 280 million years after the Big Bang. Nitrogen requires multiple generations of stars to produce in significant amounts. There simply was not enough time. One explanation is that population 3 stars were even more massive and more numerous than estimated. Supermassive stars, millions of times the mass of our Sun, burning through their fuel at a prodigious rate and dying young, scattering their processed elements into the cosmos almost immediately. This connects directly to the little red dots. If some of those massive stars collapsed not into ordinary stellar remnants but directly into black holes, bypassing the normal stellar death process entirely, they would produce both the early heavy elements and the early supermassive black holes that the telescope is finding. Another explanation involves direct collapse black holes, gas clouds in the early universe that skipped the star formation stage entirely and collapsed under their own gravity into massive black holes. These objects, if common in the earliest epochs, would explain both the unexpectedly early supermassive black holes and the rapid quenching of some galaxies. A massive black hole at the center of a young galaxy could heat the surrounding gas so intensely that star formation ceases, producing a dead galaxy like GS9 209 in a fraction of the time conventional models require. Every anomaly taken alone could be a calibration issue, a measurement error, an incomplete simulation, a model that needs adjustment rather than replacement. But taken together, they form a pattern that points toward the possibility that the early universe operated under rules not identical to the rules running the universe today. And the people whose careers depend on the current model are now facing the most uncomfortable question of their professional lives. That human dimension of the crisis is where we go next. Chapter 11. The scientists whose world is breaking. Science is practiced by human beings, and human beings are not dispassionate, calculating machines. They have careers, they have reputations, they have students and collaborators and funding agencies. They have spent decades mastering the intricacies of a particular theoretical framework. They have built their professional identities around the assumption that the framework is correct. And when the data starts suggesting that the framework may be fundamentally incomplete, the response is not purely intellectual. It is emotional. It is personal. It is deeply, unavoidably human. One senior cosmologist, reflecting on the cascade of anomalies emerging from the James Webb Space Telescope, described the experience not as excitement, but as vertigo, like standing on ground you trusted completely and feeling it move beneath your feet. The Lambda-CDM model is not just a professional tool for these researchers. It is the structure through which many of them have understood reality for 30 or 40 years. It is the lens through which they see the cosmos, and the lens is cracking. The tension is visible at conferences. Presentations of new results are followed by pointed questions from the audience. Comment sections in journal papers carry an edge that was absent a decade ago. Senior researchers who once dismissed alternative ideas are now sitting in the front row at talks about modified gravity and evolving dark energy, listening carefully, taking notes. Junior scientists are finding that proposals exploring heterodox ideas, proposals that would have been career risks 5 years ago, are now being funded. This is what genuine scientific crisis looks like from the inside. Not a dramatic collapse, not a sudden revolution, a slow grinding discomfort as the evidence accumulates and the conventional explanations stretch thinner and thinner. Most scientists are cautious by nature. They know that anomalies often dissolve when better data arrive. They have seen exciting hints evaporate before. They are trained to be skeptical, to demand overwhelming evidence before abandoning a successful model. And Lambda-CDM has been extraordinarily successful. Walking away from it requires more than a few puzzling observations. It requires a weight of evidence so heavy that the old framework simply cannot bear it. We are not there yet. But we are closer than we have been since the model was established, and the pressure is coming from multiple directions simultaneously. That is what makes this moment different from previous challenges to Lambda-CDM. In the past, individual anomalies could be addressed individually. A galaxy too massive here could be explained by better simulations there. An unusual expansion measurement could be attributed to systematic errors. But the James Webb Space Telescope has produced a constellation of anomalies that span different observations, different techniques, different redshifts, and different physical scales. Addressing them one at a time is becoming increasingly difficult when they all seem to be pointing in the same direction. And in the midst of this uncertainty, a minority view that has lingered at the edges of cosmology for 4 decades is growing louder. In 1983, an Israeli physicist named Mordechai Milgrom proposed a radical idea. What if there is no dark matter? What if instead gravity itself works differently than Newton and Einstein described? Specifically, what if, at very low accelerations, the kind experienced by stars at the outer edges of galaxies, far from the gravitational center, gravity is slightly stronger than Newtonian physics predicts? Milgrom called his framework Modified Newtonian Dynamics, or MOND. It is a deceptively simple idea. Below a certain acceleration threshold, roughly 1/10 billionth of a meter per second squared, gravity does not fall off as quickly as Newton's inverse square law predicts. It falls off more slowly. This single modification, with a single new parameter, reproduces the flat rotation curves of galaxies without invoking any dark matter at all. For decades, MOND was a fringe idea. It had vocal supporters, but was largely ignored by mainstream cosmology. The reasons were understandable. MOND worked beautifully for individual galaxy rotation curves, but struggled to explain the cosmic microwave background, galaxy cluster dynamics, and large-scale structure, all of which seem to require dark matter. Lambda-CDM, with its dark matter component, explained all of these things. MOND explained only one. In a contest between a theory that explains everything and a theory that explains one thing very well, the broader theory usually wins. But several of the James Webb Space Telescope's observations have given MOND advocates new ammunition. Small, isolated galaxies in the early universe, galaxies that should not have significant dark matter halos, show more rotational structure than Lambda-CDM predicts. Their internal dynamics look more like what MOND would produce. In MOND, galaxies do not need dark matter halos to rotate the way they do. Gravity does the job on its own at low accelerations. If these early galaxies genuinely lack the dark matter halos that Lambda-CDM requires, MOND offers a cleaner explanation. Hybrid models are now being explored. Perhaps dark matter exists, but is less dominant than Lambda-CDM assumes. Perhaps modified gravity fills part of the structural role that dark matter was thought to play exclusively. These hybrid approaches were once considered unnecessary complexity. Now they are being taken seriously by researchers at major institutions, published in peer-reviewed journals, and discussed at mainstream conferences. The minority has grown since the James Webb Space Telescope launched. Not into a majority, not yet, perhaps not ever, but the conversation has shifted. The question is no longer whether Lambda-CDM will survive intact. The question is how much of it will survive and what will replace the parts that do not. This is exactly the state of productive chaos that precedes major advances in science. Multiple competing frameworks are being developed simultaneously. None is confirmed, all are being actively tested. And the one that ultimately wins will not just change astrophysics. It will change how we understand our place in the universe. Those competing frameworks, and what each one proposes, are where we go next. Chapter 12. 4 competing theories for a new universe. When a scientific model begins to crack, theorists do not sit idle. They start building alternatives. And right now, in departments of physics and astronomy around the world, at least 4 serious theoretical frameworks are being developed to explain what the James Webb Space Telescope is showing us. None has been confirmed. Each has strengths and weaknesses, and the competition between them is one of the most intellectually exciting episodes in the history of cosmology. Think of it like a jigsaw puzzle. For decades, Lambda-CDM gave us a picture that seemed nearly complete. A few pieces were missing in the corners, but the central image was clear. Now the James Webb Space Telescope has handed us a box of new pieces, and some of them do not fit the existing picture. The question is whether we need to adjust the existing puzzle, rearrange a few sections and force the new pieces in, or whether we need to accept that we have been assembling a different puzzle entirely. The first framework is the most conservative. It proposes non-standard initial conditions. The idea is straightforward. The inflationary period, the fraction of a second after the Big Bang when the universe expanded faster than light, may not have produced perfectly random density fluctuations. The seeds of galaxy formation may have been distributed in ways that allowed faster growth in some regions. Perhaps certain areas of the early universe received a head start, denser seeds that collapsed more quickly into the halos and galaxies we observe. This approach keeps most of Lambda-CDM intact. The equations remain the same. The ingredients remain the same. Only the starting conditions change. It is the least dramatic option, but it requires an explanation for why the initial conditions deviated from the predictions of standard inflation, and that explanation is not yet in hand. The second framework introduces new physics in the dark sector. Two ideas fall under this umbrella. The first is early dark energy. This proposes that a distinct form of dark energy existed briefly in the infant universe, before the cosmic microwave background was released. This extra energy would have altered the expansion rate during a critical period, changing the predicted value of the Hubble constant derived from the cosmic microwave background and potentially resolving the Hubble tension. Early dark energy models are mathematically well defined and have been tested against the cosmic microwave background data. Some versions fit the data well. Others introduce new tensions of their own. The debate is active. The second idea under this umbrella is interacting dark matter. Standard Lambda-CDM assumes that dark matter particles interact with each other and with ordinary matter only through gravity. But what if they have additional interactions? Weak self-interactions between dark matter particles would change the internal structure of dark matter halos. The cores of halos would be smoother and denser. The rate at which halos merge and grow could be altered. Self-interacting dark matter models have been studied for years, primarily to address discrepancies at the scale of dwarf galaxies, where Lambda-CDM predicts cuspy halo cores that observations do not always confirm. The James Webb Space Telescope's early galaxy puzzle gives these models new relevance. If dark matter self-interactions allow halos to form differently in the high-density environment of the early universe, they could explain why galaxies assembled faster than standard simulations predict. The third framework is the most dramatic among the observationally motivated options: evolving dark energy. The DESI results, suggesting that dark energy may be weakening over time, open the door to quintessence models, in which dark energy is not a cosmological constant, but a dynamic field that changes with cosmic epoch. If confirmed, this would be a paradigm shift. The entire history of the universe would need to be recalculated with a time-varying dark energy component. The rate of structure formation, the ages of the oldest objects, the relationship between the cosmic microwave background and the present-day universe, all would shift. The universe's future would change too. Instead of the relentless acceleration toward an empty, frozen heat death, other endings become possible. The acceleration could slow. The universe could eventually contract. The cosmos could undergo cycles of expansion and contraction, as some models propose. This connects to the fourth and most speculative framework: theories about what came before the Big Bang. For decades, the question itself was considered meaningless. The Big Bang was the beginning. There was no before. But several serious theoretical proposals now challenge this assumption. Roger Penrose, the Nobel Prize-winning physicist, has proposed conformal cyclic cosmology. In this model, the universe undergoes an infinite series of cycles, each beginning with a Big Bang and ending with a vastly expanded, cooled state that mathematically resembles the conditions of the next Big Bang. The cycles connect. The end of one universe becomes the beginning of the next. Penrose has claimed to find evidence for this in anomalous circular patterns in the cosmic microwave background. Patterns he interprets as the gravitational signatures of black hole collisions in a previous cycle leaking through into our own. Loop quantum gravity, an approach to quantum gravity developed independently of string theory, suggests that the Big Bang was actually a big bounce. The universe contracted from a previous phase, reached a minimum size governed by quantum effects, and then expanded again. In this picture, there is no singularity, no moment of infinite density. The universe has existed for far longer than 13.8 billion years, oscillating between expansion and contraction. These ideas are not fringe. They are published in peer-reviewed journals by researchers at leading institutions. They are being taken seriously in a way they were not a decade ago, precisely because the James Webb Space Telescope keeps finding evidence that the standard picture is incomplete. When the conventional model is working perfectly, exotic alternatives attract little attention. When the conventional model is under stress, scientists become more willing to listen to ideas that once seemed too radical. Dan Skolnick of Duke University captured the mood. When there is one thing, you could rule it out as people making a mistake. When there is a second thing, you are like, okay, maybe something weird is going on. Something weird is going on. The competing frameworks all share one recognition. Something in the Standard Model is missing. The puzzle is not yet solved. The new pieces have not yet been placed, but the picture is changing. And while physicists debate the large-scale structure of reality, the James Webb Space Telescope has been turning its instruments towards something much closer. The kinds of environments where planets form. And what it found there changes the context of everything else in this story. Chapter 13, The Search for Life in a Stranger Universe. While the James Webb Space Telescope has been dismantling assumptions about galaxies, dark energy, and the expansion of the universe, it has also been doing something quieter. Something that may ultimately matter more than any cosmological model. It has been sniffing the atmospheres of planets around other stars. And what it has found there has moved the question of extraterrestrial life from philosophy to measurement. In the Orion Nebula, one of the most intensively studied stellar nurseries in the sky, the James Webb Space Telescope discovered something unexpected. Rogue planets. Planet-sized objects drifting through space without a parent star. Not one or two. Dozens of candidates. Some of them appeared to be traveling in pairs, binary planet systems, gravitationally bound to each other, but orbiting nothing. These objects were not predicted. Their existence suggests that planet formation is a more abundant and more varied process than anyone assumed. Planets do not only form in the orderly disks around young stars, they form everywhere. They form in excess. They get ejected. They wander. The universe makes planets with a profligacy that borders on extravagance. Then the telescope turned to a planet called WSP-39b, a gas giant orbiting a distant star. In its atmosphere, the James Webb Space Telescope achieved a milestone. The first clear detection of carbon dioxide in the atmosphere of a planet outside our solar system. The measurement was precise. The signal was unambiguous. And it demonstrated something crucial. The James Webb Space Telescope can identify specific molecules in the atmospheres of worlds orbiting other stars, worlds trillions of miles away. By analyzing the starlight that filters through their thin, gaseous envelopes. This is spectroscopy at its most extraordinary. When a planet passes in front of its host star, a tiny fraction of the starlight passes through the planet's atmosphere on its way to us. Different molecules absorb different wavelengths. By measuring which wavelengths are absorbed and which pass through, astronomers can determine what the atmosphere is made of: carbon dioxide, methane, water vapor, ammonia, and potentially molecules that have no business being there unless something is producing them. Molecules that on Earth are produced exclusively by living organisms. Which brings us to a planet called K2-18b. This world orbits a red dwarf star, 124 light-years from Earth. It sits in the habitable zone, the region around a star where temperatures could allow liquid water to exist on a planet's surface. It is roughly 8.5 times the mass of Earth. It may be a Haitian world, a planet with a hydrogen-rich atmosphere overlying a global ocean. It is one of the most promising candidates for harboring conditions compatible with life. In April of 2025, a team led by Niku Madhusudhan at the University of Cambridge reported a detection that sent shockwaves through the scientific community. Using the James Webb Space Telescope's mid-infrared instrument, they found evidence of dimethyl sulfide in the atmosphere of K2-18b. Dimethyl sulfide is a molecule that on Earth is produced exclusively by marine microorganisms, primarily phytoplankton. It has no known significant abiotic source. If dimethyl sulfide exists in the atmosphere of another world, the most straightforward explanation is biological. The detection was at 3 sigma statistical significance. That means there is roughly a 99.7% probability that the signal is real. The concentrations were enormous, thousands of times higher than on Earth. Madhusudhan described the significance of the moment. "We have entered a new era in the search for life beyond Earth where it is possible to detect and debate about potential biosignatures," he said. "This is unprecedented, but science demands scrutiny." And in July of 2025, a NASA-led reanalysis of the same data reached a different conclusion. The team argued that the signal attributed to dimethyl sulfide could be explained by red noise, random statistical fluctuations in the data that mimic a real signal. They found insufficient evidence to confirm the detection. The debate is fierce and ongoing. The Cambridge team stands by their analysis. The NASA team stands by theirs. Other groups are conducting independent analyses. Additional observations have been proposed. The James Webb Space Telescope may observe K2-18b again, with different instruments to test the signal from a different angle. And this is the point. The controversy itself is the milestone. We are now at a stage in the history of science where we can detect potential biosignatures in the atmospheres of planets orbiting other stars and argue about whether they are real. 10 years ago, this was science fiction. 5 years ago, it was aspirational. Today, it is happening. The instruments exist. The data exist. The debate is between competing interpretations of real observations, not hypothetical scenarios. Nicole Colon, a NASA exoplanet scientist, reflected on how quickly the field has advanced. "I did not expect it so soon into the mission," she said, "or just so easily." Now zoom out. Consider the full picture the James Webb Space Telescope has painted. The universe builds structure faster and more efficiently than anyone predicted. Galaxies form earlier, stars ignite sooner, black holes grow more rapidly. Heavy elements appear in quantities that suggest stellar evolution operates at speeds our models did not anticipate. If the universe is more efficient at building complexity than we thought, that efficiency extends to planet formation too. More galaxies forming earlier means more generations of stars. More generations of stars means more heavy elements. More heavy elements means more rocky planets. More rocky planets means more potential homes for life. And earlier in cosmic history, either life is common, a natural consequence of a universe that builds complexity with the profligate efficiency the James Webb Space Telescope has revealed, a process running for billions of years across billions of galaxies in billions of potential locations. Or life is rare, an improbable accident that occurred on one pale blue dot orbiting an ordinary star in an unremarkable galaxy. And we are alone in a cosmos so vast that the distance between us and the nearest living thing is greater than the space between stars. Either possibility is extraordinary. Either possibility should keep you up at night. And either way, we will not know the answer by sitting still. The James Webb Space Telescope will not resolve whether we are alone. But it has moved the question from philosophy to measurement. And the instruments being built right now, designed specifically in response to what the James Webb Space Telescope has found, will push even deeper into both the cosmic structure question and the life question. Those instruments and what they will reveal are where we go next. Chapter 14. The universe has never been smaller than we thought. We have traveled a long way tonight. From the tiny red dots scattered through the James Webb Space Telescope's first deep field images, to the fundamental constants that may or may not be constant at all. From galaxies that formed before they should have existed, to a number that governs the fate of the cosmos and refuses to settle on a single value. From the invisible scaffolding that holds everything together, to the invisible force that is pushing everything apart. And from the atmospheres of distant worlds, to the possibility that we are not alone. Now, Let us sit with what we have learned. Not to draw conclusions. The data do not yet support conclusions, but to feel the weight of the question, because the question itself is worth holding. The universe is not what we thought it was, not in the details, not in the broad strokes. The Standard Model of Cosmology, the most successful mathematical framework in the history of science, is under pressure from every direction. The galaxies are too massive. The expansion rate disagrees with itself. Dark energy may be evolving. The structures are too large. The cosmic microwave background has unexplained patterns. The first stars and black holes formed too fast. The laws of physics may not be as fixed as we assumed, and 95% of everything remains unexplained. None of this means the Standard Model is wrong. It means it is incomplete. There is a difference. Newton's laws of motion are not wrong. They are incomplete. They work perfectly in everyday situations but fail at very high speeds and very strong gravitational fields, where Einstein's general relativity takes over. General relativity is not wrong. It is incomplete. It works perfectly at large scales, but breaks down at the quantum level, where a theory of quantum gravity is needed. Each framework is a step on a staircase that ascends toward a deeper understanding. Each step is built on the one below it, and each step, when we reach it, reveals that there is another step above. That is the pattern of science. Careful observations reveal accumulated anomalies. The anomalies resist conventional explanation. Theoretical chaos ensues as competing frameworks vie for dominance. And then, eventually, sometimes decades later, a breakthrough emerges that resolves the tension and opens an entirely new vista. Newton revealed the question of what gravity is. Einstein answered that question and revealed the deeper question of how gravity relates to the geometry of space-time. Whatever comes next will answer the questions the James Webb Space Telescope has raised and reveal questions we have not yet thought to ask. We are inside one of these moments right now. The anomalies are accumulating. The theories are competing. The instruments are improving. And the next generation of telescopes will push even deeper. The extremely large telescope is under construction in the Atacama Desert of Chile. When completed in the late 2020s, its primary mirror will span 130 feet, making it the largest optical telescope ever built. It will be capable of directly imaging the atmospheres of rocky exoplanets, analyzing their chemical composition in detail that the James Webb Space Telescope cannot achieve. If there are biosignatures in the atmospheres of nearby Earth-like worlds, this telescope will be among the first instruments capable of detecting them. The Nancy Grace Roman Space Telescope, NASA's next great space observatory, completed construction in November of 2025 and is on track for launch in the fall of 2026. Its field of view will be 200 times larger than the Hubble Space Telescopes, allowing it to survey billions of galaxies across vast swaths of sky. In its first 5 years of operation, it is expected to discover more than 100,000 exoplanets, map hundreds of millions of stars, and observe billions of galaxies. Julie McHenry, NASA's senior project scientist for the Roman telescope, described the scope of the mission in terms that bear repeating. The sheer volume of data will transform our understanding of cosmic structure, dark energy, and planetary systems in ways we cannot yet fully anticipate. The CMB-S4 project, a ground-based array of telescopes being deployed across the South Pole and the Atacama Desert, will map the cosmic microwave background with 10 times the precision of the Planck satellite. If the anomalies in the oldest light are real, CMB-S4 will confirm them beyond doubt. If they are statistical flukes, it will lay them to rest. Together, these instruments will deliver more data about the fundamental structure of the universe in the next 15 years than the previous century combined. The questions the James Webb Space Telescope has raised will be answered. Not all at once, not neatly. Science does not work that way. But the answers are coming. And here is the thing that matters most. The thing that every discovery the James Webb Space Telescope has made reinforces. The universe has never, not once, in the entire history of human investigation, turned out to be smaller than we thought. It has never been simpler. It has never been less interesting. It has never confirmed that we had finally reached the end of questions. Every time we built a better instrument, every time we looked more carefully, every time we measured more precisely, the universe expanded. Not just in physical size, but in complexity, in strangeness, in the depth of its mysteries. Galileo pointed a telescope at Jupiter and found moons. Hubble measured distant galaxies and found the expansion. Penzias and Wilson detected the cosmic microwave background and found the echo of creation. The James Webb Space Telescope looked deeper than any instrument before it and found a universe that refuses to match its own description. That refusal is not a failure. It is an invitation. An invitation to look again, to measure again, to think again, to sit in the quiet, in the dark, and ask the questions that have no comfortable answers. Right now, 1 million miles from Earth, at a point in space called the second Lagrange point, where the gravitational pulls of the Earth and the Sun balance perfectly, the James Webb Space Telescope is still out there. Its golden mirror, 18 hexagonal segments of beryllium coated in a layer of gold thinner than a human hair, is still pointed at the sky, still collecting photons, still gathering light that has been traveling for billions of years across an expanding cosmos. Ancient light. Light from the first galaxies. Light from the first stars. Light from an era when the universe was brand new and everything was just beginning. And in that light, the universe is still speaking. It is saying something we have not yet fully understood. Something about its origins. Something about its structure. Something about the laws that govern it and the forces that shape it and the strange, magnificent, terrifying complexity of a cosmos that builds black holes inside stars, forms galaxies before the rules say it can, accelerates its own expansion for reasons no one can explain, and maybe, just maybe, scatters life across its surface like seeds on fertile ground. We are listening, we are watching, we are asking, and the universe, as it always has, is answering with more than we expected, more than we predicted, more than any model we have ever built could contain. The universe has never been smaller than we thought, and it never will be. If you enjoyed this deep investigation into the cosmos, please like this video and subscribe to the channel. Your support makes these detailed explorations possible. Tell me in the comments, what do you think is the most significant discovery the James Webb Space Telescope has made? Do you think dark energy is truly evolving? And do you believe we will find evidence of life beyond Earth in our lifetime? These are not just questions for scientists, they are questions for all of us. Because the universe belongs to everyone who looks up. Thank you for watching. I will see you in the next investigation.